Why can't you find a shorter path to a vertex after visiting that vertex in Dijkstra's algorithm? In the last few lectures, when we were diving deeper and deeper into Dijkstra's algorithm, we kept focusing on one point, that is, Dijkstra's algorithm is a greedy algorithm, and in it, once a vertex is marked as visited and its shortest distance is finalized, the shortest distance to this vertex should never change in future. So this is what we kept focusing in Dijkstra's algorithm. Many of you would have had this doubt in mind that why is it that you can never find another shortest path after marking this vertex as visited? Why is it not possible that even after visiting, when you see through the other vertices, you may discover a new path which is reaching here in even shorter time or maybe shorter distance? Why is it not possible? This is what we are going to prove in this lecture. So first of all, in Dijkstra's algorithm, what are you doing in each iteration? In each iteration, from the list of unvisited vertices, you will pick whichever vertex is having the smallest distance from source and mark it as visited. This is what you are going to do. So once you mark it as visited, you will never reconsider it, and whatever be the final shortest distance that you have at the point of visit, that is considered as the shortest distance to this particular vertex, right? So what is the claim that we want to prove here? Our claim is that once a vertex U is visited, there cannot exist another shorter path which is having a lesser distance to U. This is the claim that we have. So let us prove this claim in this lecture. Initially, just assume for contradiction that a shorter path to U exists even after it has been visited. That is, you already marked U as visited, but you are assuming there exists a path P which is a shorter path to U than what you already found when you marked it as visited. This is what you are assuming. That is, you know about a path which is having a distance lesser than d of u. So whenever you visited u, you finalized d of u, and you are presently saying that you know some other path which is having a distance lesser than d of u, right? If this was the case, then when u was chosen, it was chosen because it was the shortest one possible. That is, let us go to the point when you chose u to visit. At that particular point, u was chosen because it had the minimum shortest distance from S, right? This is correct. Whenever you chose u, at that particular point, among the unvisited vertices, u had the minimum shortest distance from S, which means d of u was less than or equal to d of v, where v is the set of all vertices in unvisited set, right? So among all the unvisited set, at that point of time when you selected u to be visited, you had the least distance from source. This is true, you know this, because that is why you picked it in order to visit. Next thing is, this means any other unvisited node that is there in this unvisited list, that must have a distance which is either equal to d of u or greater than d of u from the source vertex S. This is the only case when you will select u to be visited. Then just suppose that there is another path which reduces this d of u, whatever be the distance to u that you found. Let us say there is some another path which is called P, which reduces this d of u. And when will it reduce? After visiting u, it is going to reduce this d of u. This means the access this alternate path P via some other vertex V. And what is a vertex V? V is in the unvisited list, right? So among the unvisited list, there is a path which goes through some vertex in this unvisited list, which is called P, the path is called P, and P is having a distance lesser than D of U to reach U. This is the point that we have right now. So you know that among the unvisited vertices, there should at least be one vertex which is involved in this path P. Because if it is not involved, then you would already have selected that right when you selected U to be visited. So because you were not able to select it when you were visiting U, that means this particular path P has at least one among the unvisited vertices involved. That is the only reason why you were not able to find this path when you were selecting U in order to visit it, right? But just think about it, that if P really gave a smaller path, then V should have been selected before U. Why is it? Because why did you select U? This is the whole point. Why did you select U? Because U had a distance which is lesser than or equal to the distance from any other vertex among unvisited vertices. Now you are saying that there is a path which goes like this. It reaches, let me draw this here. Let us say this is my source vertex, okay? And I am saying there is some path which reaches U. This is my present shortest path to U which I have selected. What is my new claim? That there exists a path P which is, let us say, going somewhere like this, and it reaches a vertex V, and after visiting V, through V it reaches U. This is the only way this path P can exist without being selected when U was initially picked, right? If this is the case, that means distance to this vertex V should be either equal to U or less than U. That is, even if you consider that V to U distance is 0, still the distance till V should be at max distance to U, or ideally it should be lesser than the distance to U. And if you know that V is having a distance lesser than U, then U should never have been picked at the first place, right? You should have picked U. Instead, you should have picked V, because V is in the unvisited set and V is having a shorter distance from source vertex than U. Then how can you select U? That selection itself is wrong, which means this contradicts the fact that U was already the smallest unvisited node. Smallest in the sense shortest distanced, right? So initially this was your assumption that U is the node which had smallest distance from the source, and your present assumption that the existence of V through which you can find a path to U which is smaller than D of U contradicts the fact that U was already the shortest distanced unvisited node. Hence, your assumption that a shorter path can appear later is incorrect. It cannot stand, and because of this, our claim is right. That means you cannot find a shorter path to a vertex after visiting it in Dijkstra's algorithm. One thing that you have to keep in mind is, even in the previous lecture we discussed about this, that if there are negative weighted edges, in that case none of these things hold. Even the whole Dijkstra's algorithm won't work. So in case there are only positive weight edges, then whatever we discussed here, everything holds and our claim is right. But if there are negative weight edges, all these won't work. The whole Dijkstra's algorithm won't work in that case, right?